Hello everyone, and thank you for being here. We hope everyone is doing well, and we hope you will enjoy our webinar today, introducing the VSP-P1 Nanostructured Material Printer, the ultimate tool for material development. My name is Andrei Ilinka, content creator for VSPARTICLE, and I will be your virtual guide through today's webinar. For this session, our aim is to get you acquainted with the possibilities and the technology behind our nanostructured printer. And the best way to get this across to you is through a combination of a classical webinar presentation and a virtual lab experience. Behind the presentation, we have Pauline Roos presenting the ins and the outs of our printer. And in the virtual lab, we have Koosje Pothoven, who will walk you through the use of the printer. But first, please let me take you through the flow of today's webinar. I will first walk you through the webinar interface and discuss how we are going to handle the questions during the presentation. Webinar recording, we will let you know about upcoming events and ways in which you can get in touch with us. I'll provide a short VSPARTICLE introduction for people who are not yet familiar with our company before I hand out this presentation to Pauline and Koosje. The last session of the webinar is in charge with answering your questions. We are taking questions during the webinar and we'll try to answer all of them after the presentation has ended. For the questions that remain unanswered, we will do a follow-up email. You can find the chat room in your bottom right corner, the icon with the question mark. This webinar session will be recorded and we will send you a link in the coming days so you can share it with your colleagues or watch it later. We have two more upcoming events: size-dependent particle property screening made simple with the VSP-S1 size selector, and novel-supported catalyst development, the VSP-PC powder coater, which is the latest addition to our product portfolio. For the dates, we will send up a follow email or just follow us on LinkedIn or on website, where we will announce when this event will start. We do have additional information that we're happy to provide. We would like to have feedback from you, and this information will help us understand how we can best support your research. So if you are curious about upcoming events and you have maybe webinar suggestions, you can contact our communications department via our contact person, which is myself, Andrei Ilinka, a.ilinka@vsparticle.com, or by phone number, international prefix 0633891908. If you want to know more about VSPARTICLE solutions and how they can help you in speeding up your research, you can contact our sales department via our contact person, m.comp@vsparticle.com, or by phone at international prefix 0883080413. Unlocking the full potential of new materials and empowering material pioneers is at the core of VSPARTICLE. Born out of the research labs of TU Delft with over 20 years of experience in the synthesis of aerosols, VSPARTICLE believes there is a whole new world of possibilities at the nanoscale. As we all start to understand these possibilities, it will enable research and industry to rethink production processes and develop new materials to create innovative applications. At VSPARTICLE, we support this process by making nanoparticle-based manufacturing as easy as pushing a button and providing research and industry with the tools to rapidly advance the field of nanotechnology. Since 2014, we have helped scientists and industry leaders around the world to reduce the development time of new materials and applications in important fields such as semiconductors, sensors, catalysis, healthcare, and batteries. The team behind VSPARTICLE is comprised of 20 young, passionate people and is headquartered in Delft. We have now an international distribution network in the USA, Europe, and Asia, and here you can see a map of the installed base of VSPARTICLE R&D system. Thank you for following me through this introduction, and before I give the microphone to Pauline, I would like to remind everyone that you are on mute during this live session, so you won't be able to speak. Please address your questions and observations in the chat box, and we will address them at the end of the session. The duration of today's webinar will be around 40 minutes, including the Q&A, but we'll leave the event open for a few more minutes so you can have a chance to ask all of your questions. That was it from me now. I will hand out to Pauline and Kosje, and I will talk to you again during the Q&A session. Enjoy. Pauline, you have the floor.
Welcome, everybody. Good morning, and my name is Pauline Roels. For the last 2 years, I've been working on the development of the printer and also worked a lot with the system in the lab. And I will give this webinar together with my colleague Kosje on the VSP-P1 Nanostructured Material Printer. The VSP-P1 Nanostructured Material Printer is a research tool that allows you to locally deposit nanoporous thin films. Why is this unique? It combines the advantages of additive manufacturing with the purity of thin film deposition. Because you can locally deposit the material, you remove the need to do masking or edging required for instance, physical vapor deposition techniques like sputtering. And if you compare it with inkjet or other wet chemical synthesis methods, you will never get the same purity as you have to deal with solvents or adhesions or surfactants to be able to print the material. Plus, getting to the right recipe could also take months of work. How do we do it? Our process is based on a gas phase process. We developed a system where the generation of the nanoparticles in an aerosol, the characterization of the particles, and the deposition of the particles is integrated in one continuous process. This process only requires target material, a carrier gas, and electricity. So we start with a bulk metallic targets, from which we create nanoparticles in a gas, and then we deposit the particles and we can create nanostructured materials. Our printer consists of 2 systems actually. So it's the VSP-G1, which is the source of all our products, and the VSP-P1, which is the printer. So I will first explain a bit about the technology behind the VSP-G1. Afterwards, we give you a short demonstration, and then I'll continue with the printer. The generation of nanoparticles is based on spark ablation. It is based on a physical phenomenon that only requires electricity, a carrier gas, and electrode material. Within the reactor chamber, 2 electrodes of the desired material are mounted opposed to each other with a small gap between them, and a carrier gas flows through that gap. A high power is set over the electrodes, and when the energy is discharged through a plasma channel, the temperature is so high that it immediately evaporates material from the electrodes. The created vapor of singular atoms is taken along by this carrier gas and transported out of the system. During this residence time, the atoms collide and form bigger particles and tend to agglomerate along the way unless sufficiently diluted. The nanoparticles are pure, they're free of solvents or any organic compounds, and have general particle size of sub-20 nanometer. And the whole process is under atmospheric pressure, and the current production is milligrams per hour. Here you can see an overview of all the elements that are compatible with spark ablation. So any metals, alloys, or semiconductors can all be processed, that can be processed into electrodes, can be used in this machine. Moreover, you have the option to mix material. So if you use 2 of the same electrodes, you get that material. But if you combine 2 different electrodes, you get a composite of those 2 materials. And you can also use alloyed electrodes. If you have a second G1 integrated in the setup, this will allow you to have even more freedom with the different materials. So you can do sequential deposition while you first print one layer of material and on top of it another layer, or you can mix the gas streams parallel or in series before you deposit them. This way you can create core shell particle structures or really have an composition, and there you can also adjust the ratio. What you could also do is add a reactive gas through the carrier gas, for instance, an oxygen, and then you can create metal oxides or nitrides. Here you see an image of an electrode mounted in our system. So I will now hand over to the virtual lab to Koosje, where she will demonstrate how easy it is to install the electrodes and change the material.
Hello everyone, and welcome to the virtual lab. Thank you for joining this live demo. My name is Koosje Pothoven, and soon I will introduce you to the nanostructured material printer. First, we will need to assemble the VSP-P1 nanoparticle generator, since this is of course at the heart of our printer system. The VSP-P1 consists of two parts. Its base unit is already at the printer, and its reactor head is laying in front of me. And I will walk you briefly through the assembly of this piece and then mount it on the printer. All we need to do for the assembly of the reactor head is choose some electrodes that we would like to spark with. Today I am taking silver. And these electrodes we click into the electrode holder. Then I take an assembly stage to nicely align the reactor head so it will fit easily onto the base unit. And all we need to do is connect the two pieces with a true flow piece. Connect them using an O-ring, and I do the same on the other side. When this is done, we can go to the printer to assemble it onto its base units. So I'm currently standing next to the nanostructured material printer. I just mounted the reactor head onto the G1 base unit and screwed it down with some pins to make sure we have proper connection. Now I can turn on the G1 and it will start aligning the electrodes. When it has found the proper distance between the electrodes, it will be ready to spark. On the back of the true flow piece, I can attach the carrier gas inlet. And on the front, where we have the nano aerosol outlet, we can attach it to the tubing of the printer. So our aerosol will flow into the vacuum chamber where it will be impacted on your substrate. Later on, I will show how to place substrates and print patterns. First, I will hand you back over to Pauline, who will tell some more about the printer.
Hi, so the nanoparticle deposition is based on inertial impaction. The as you can see on the top of the vacuum chamber, the nanoaerosol flows into the system, and via pressure difference, the nanoparticles are accelerated through a nozzle and impacted on the substrate. We have a rough vacuum, so around 0.2 millibar while we are printing. And the current spot size ranges from 100 micron to 1 centimeter, depending on the nozzle type you use and the distance from the nozzle to the substrate. We have a 10 micron position accuracy, and via an XYZ control, we can print any type of pattern. And if we adjust, for instance, the print speed, we can adjust the layer thickness from a sparse distribution of agglomerates up to several microns thick layer. The output looks like this. So we have a nanostructured layer. We see for both metal oxides and for noble metals the same type of structure, which consists of sub 20 nanometer particles agglomerated. This material is stable under ambient conditions. And here you can see an example of a printed gold pattern on a contact lens. So for the substrate holds, as long as it fits the 15 by 15 centimeter table in the printer, you can print on it. So MEMS, chips, serre substrates, 6-inch wafer, or even flexible polymers, all substrates are possible in our device. And we control the system via our VSP control software, which allows you to remotely control the printer, give you an autonomous operation, and is very intuitive and easy to use. So you can set the spark powers, the flow rates, you can upload your pattern, and you can use the pump and start your print. The markets that we focus on are sensors, healthcare, material screening, and microreactors. So I will give you 2 examples of applications that we're working on. One is a metal oxide semiconductor gas sensor, which consists of several different components, including a heater and electrodes. But what we do is we print the top layer of the sensing material. Because this layer consists of very small particles and is highly porous, so has a high surface to volume ratio, it is very sensitive. Because we are also able to combine different materials in different ratios, we can really make the sensor print sensing arrays and make the sensor more selective. And this local deposition manufacturing actually decreases all the steps to develop a sensor, because you can locally deposit and you will not need any masks. Another example is an electrocatalysis screening project that we did together with Klaas-Jan Schouten from Avantium. Here we deposited an 8x8 dots. And we changed the nickel composition. So if you look at the graph on the left side, you have 100% iron, and then we increased the nickel. And on the vertical axis, we increased the deposition time, so the thickness of the layer. And this way you can really fast print multiple different combinations of material, and then come to a for this specific application was an oxygen evolution reactor, and they did the analysis, so we can do high throughput material screening. So now we go back to the lab, and Koosje will show how we can place your substrate in the printer and start printing.
Welcome back to the virtual lab. I will now show you how to print any pattern that you like on various substrates. Here at VSPARTICLE, we usually use substrates like Kapton foil or silicon wafers or glass plates. The printing conditions are at room temperature and rough vacuum, so as long as your substrate is not damaged in these conditions, it will be suitable to use in the printer. I will show how to print a simple pattern on this glass plate. So let's go to the printer. I placed the substrate in the printer and will now close the door tightly so no air can come in during the printing process. With a remote software control system, you can now start the pump and the spark and flow and set the settings such how we want it and upload the pattern that you want to print for a substrate. By adjusting the spark voltage and the flow rate, you can change the nanostructure characteristics like the nanoparticle size. And by adjusting the nozzle height or print speed, you can change the spot size or the layer thickness of your pattern. So let's now go to a short movie of a simple pattern of 5 lines that we printed previously. 5 lines are printed with different nozzle heights, as you can see hopefully soon. And because the nozzle height is different for all the lines, we see a different line width on those lines. And as I said, by changing the nozzle speed, you could change the layer thickness. And so you can vary various aspects of your pattern while printing. When it's done, I can again use the control software to shut down the system and flush the chamber so I can open it again and take out the sample. Thank you all for watching the live demo. I will now give you back to Pauline, who will show some more examples.
So here you see two patterns that we printed. So you see the different line thicknesses and widths and our logo that is printed. And I want to conclude with the main specifications of our printer. So with the VSP-P1 Nanostructured Material Printer, you're able to locally deposit nanoporous thin films. You can print any combination of metals and metal oxides, and the particles consist of ultra clean sub 20 nanometer particles. Please notice that this demonstration was done with the beta version of the printer. If you want more information on the commercial available printer, please contact Maarten. And now I would like to give back the word to Andrea and look forward to answering your questions. Thank you.
Thank you, Koosje, for the demonstration. So here you see some images of different substrates that we printed. And I would like to conclude with some final remarks on our printer. So with our VSP-P1, you can locally deposit nanoporous thin films. You can print any combination of metal and metal oxides. And this material is ultra clean and consists of sub 20 nanometer particles, which makes it really useful for sensing application or electrocatalysis. Thank you. I will now hand you back to Andrea, and I will welcome you all the questions.
Thank you, Pauline and Koosje, for this very interactive session. We are now ready to take your questions. You will also be able to see Pauline's face in case you are curious, as they will both answer the questions together. Okay, just give me a few minutes to arrange the questions. Okay, as you can see here, we have Pauline and Koosje. Our first question is, how do you clean the system?
I can give an answer to that. So what we do when we change the electrodes, we take this part out, the reactor chamber, and then we clean the inside of the reactor chamber. What we also clean is the nozzle, so you can screw it open, off, and then change the nozzle and also clean it in an ultrasonic bath. And the tubes we clean by flowing high flow rate through the tubes to clean it, and we do that for 15 minutes, sometimes 20. And so once every half year we might clean the whole tubes also. So that's also easy to just to disconnect the tubes on the side.
Okay, thank you. Second question. How do you align the nozzle with the substrate?
Good question. We have a nozzle, attached to the nozzle we have a microscope camera. And with this you can, from the interface, see where a nozzle is and align it exactly where you want it to be and see where the pattern will be. And then we know, of course, exactly the distance between the camera and the nozzle. And that will be, yeah, then you can print exactly where you need your material to be.
Thank you, Kosje. We are going to take a few more questions. Can you make conductive thin film? Is there a substrate heater integrated here?
No, there's no heater placed in the printer. And what we print is semiconductive material. We do sometimes heat the material up afterwards or do laser sintering. And then you can make it conductive, but it all depends on the material and application that you want to develop.
Thank you, Pauline. Just give me a few seconds to filter through the questions. For the electrodes, can we use in-house fabricated custom alloy?
Yes, as long as they are conductive, then that should be possible.
Another question. For the electrodes, can you be more specific with the resistivity ranges? You mentioned that it has to be lower than doped silicon.
But we can ask it and give you the answer.
We will follow up that question with an email because it's a very technical question and we need to think about it. Just a second. How does the alignment of the nozzle and the substrate work? I think we already answered that. How many electrodes can you use? Only 2? In order to get binary or ternary, could you give any suggestions?
So now in the system you can only use 2 electrodes, and what you can do is use 2 of different materials, but then you don't really have a lot of control on the ratio of the mixing. So if you use 2 G1s, you can really nicely control the combination of materials. And if you use an alloy, then you exactly know what particles you can print.
Thank you, Pauline. Unfortunately, our time is up, but don't worry. I see we have a lot of questions, which is we are very happy for this. It means that you have interest. We will answer them in a follow-up email, and we will also leave the event open for 10 more minutes so we can gather all of your curiosities and questions. Thank you from my side. It has been a very nice session. Thank you to my colleagues for this interactive, and I think they also want to say a proper goodbye. From my side, I'll see you in our future digital endeavors. Have a nice day and hope to see you soon. Bye-bye.
Thanks.
Thank you for listening. Thanks.